Now let us go to the next assignment, that is assignment number 15. Now in this assignment number 15 we have to write down an 8051C program to toggle all the bits of port 0 and port 1 continuously forever with a 250 millisecond delay using an logical XOR operation. So here one thing we have to underline, that we have to toggle the port 0 and port 1. So when I say toggle, it means that alternate bit should be 1 and 0, so that we have to perform. After that we have to emphasize that in between we have to have a delay of 250 millisecond delay should be there, and we have to use an XOR operation. So this program is very similar to that of that we have seen in assignment number 14. Only the thing is that we have to toggle the bits and we have to use an XOR operation. So let us look at the program for the assignment number 15. So here in this slide you can see that the program for assignment number 15, and here you can see that now I am assigning P0 as 0x55, which is nothing but the bit pattern of 0101, and similarly at P1 also I have given the bit pattern of 0x55, which is nothing but also 0101. So before you are using an operator, we have to assign some values. So once the values are assigned, and then we can operate those on the binary operator or binary operators like an XOR. Now within the super loop you can see that P0 is equal to P0, and the cap sign is nothing but for the XOR operator P0 cap 0xFF, means whatever is the value within a P0 that will be XORed with the 0xFF, which is nothing but all ones. And same process is done with the port 1, and after that we are calling a delay of 250 millisecond delay, and we will repeat this forever. And to generate this delay we have wrote down a subroutine for the 250 millisecond delay. Now let us look at how this program works in Kill Compiler. Now let us go to the Kill Compiler, and within a Kill Compiler now we want to add the assignment number 15. So here is your assignment number 15. So I would like to remind you that I have already given you all these files in a tutorial, that is a microvision tutorial video. So you can go to that tutorial video and you can download all these working programs. Now here is a program by which we are going to toggle all the bits. So what I was saying is, when you assign a port 0 as 0x55, which is nothing but, I will comment this, that is 0101. So this is the pattern that we are going to apply, 0101. And same is for the port 1. So these are the initial values that we are going to apply, and after that we are going to XOR these values with all ones. So this is 1 1 and 1 1 1. Okay, so can you imagine what will happen if I XOR these values with 55? So here at the bottom I will give you the logic. Okay, so what happens is that, so first of all the data is 0101 0101, and after that what we are doing is we are performing an XOR operation with what? With 1111, okay, and 111 and 1. So what is the net result? So I'll write down a net result over here. So you can, as you can imagine that, I'll go from D7 bit, so it is better to write down me on the compiler. So when the bits are similar, the output is 0. When the bits are dissimilar, the output is 1. So here, if I apply the rule for D7, here the bits are dissimilar bits, so the output is 1. Next we have the similar bits, so output will be 0. Next to that we have the dissimilar bits, so the output is 1. So you can imagine that we are getting the output of 1 0. After that we are getting one more 0, 1 0 1 and 0. Just take a time and recall your XOR truth table. So this is going to be an output in the next cycle, and to that next cycle what will happen? Once again, as this is an infinite loop, it will XOR this data with the all ones. Now what will happen with the next cycle? You can look at over here. So this is my data at port, and we are going to XOR with all number of ones. So once again you can check out the solution for this. Similar bit means 0 and dissimilar bit means 1. So this is just a pattern 0 1 0 1 0 1. So that is the output. And you can imagine that this is just a cycle. So this is my 0x55. This was a constant that we are dealing, that is 0xff, and here you can see that output data is nothing but, as you can imagine, that 0xaa. So once again, if you XOR that, you will get 0x55. Sorry, 0x55. Once again, you XOR this data with the constant data of 0xff. In the next cycle, you will get the data of 0xaa. And what is meant by the 0xaa? It means that we have 1010 bit pattern. So this is how the logic works. So this is the logic behind this program to toggle all the bits by using an XOR operation. So let us try and simulate this program. So first of all, I'll save this and I'll compile it. So 0 error, 0 warning. So I will keep this for the reference. We will go to the start stop debug session. Okay. So once again, we require port 0 and port 1, as in assignment number 14 we have already run this, so that is why we are getting port 0 and port 1. Now if you are not looking at port 0 and port 1, then you have to go to the peripherals, and from the peripherals you can add a number of ports. So let us try and simulate this program in a stepwise manner. So first of all, the program will assign the 0x55 value to these ports. So this is a 55 value, and that is applied to the port 0, and in the next cycle it is applied to the port 1. Now it will perform an XOR operation, and as soon as it performs an operation, XOR operation, the data will be available on port 0. So here you can see that we are getting 0xaa, and with the next line it will go assign the values of 0xaa. So if I go on doing this, okay, so it will take a time because we have used a delay. Now instead of that, I will run this in a continuous manner. So here you can see that the bits are toggling. So we have just performed this operation by using an XOR. So either you can go with the NOT operation or either you can go with the XOR operation. The results are very same. The results are very same. Now here in the previous program we have generated a square wave. Here we are just toggling the bits. So we can, instead of assigning the values of zeros and ones, even we can use an XOR operator, or you can use a NOT operator. So I'll stop this program and I'll come out of this debug mode, and this was for assignment number 15. Now let us look at the assignment number 16. In assignment number 16, what we have to perform is we have to observe the port number 2.7, and then we have to read this switch, and we have to complement the switch, and we have to send the data to the port 1.0. Now why we have to complement this bit? If you look at the architecture of this program, the architecture of this hardware is that we have a pull-up resistor. So whenever you are having a pull-up resistor, whenever the switch is off, by default it will give you the logic of 1, and whenever your switch is on condition, by default it will give you the output as a logic 0. So that condition is exactly reverse. So switch is off, it will give you a VCC value, that is 5 volt. So switch is on, it will give you the value of 0 volt, and which is nothing but a logic 0. So we have to reverse this logic. So when I say we have to reverse this logic, in which that means that we have to use a NOT operation. So let us look at the program. Now here is the program for assignment number 16. I would recommend you that you should pause the video and you should look at and try to understand this program before I should explain this program. Once you can understand this program on your own, you will be able to write down your program. So let us look at this program first. This was a tip. So in this case we require 3 S-bit variable. One variable for the LED, the second variable for the switch, and the third variable to store that data. So once you read the switch, we have to store that data, and after that we have to perform the operation. So here I have used a S bit, my bit 1 is equal to P1.0, where I am going to connect an LED. S bit, my bit 2 is equal to P2.0, where we are going to connect a switch, and we are using a third variable to store that data, that is bit, my bit 3 is equal to 0x20. So this is an address where this data is going to be stored. So all these three are the single bit variables. After that we have a void main void, and after that we are using my bit 2 is equal to 1. Now why we are passing a 1 to my bit 2? Because we want to make this port 2 line number 7 as an input line. After that I have used a for loop as a forever loop. Similar to that of while 1, we can use a for loop as a forever loop. If you are not giving any initial condition and the final condition, we can use this as a forever loop. When within the forever loop, what we are doing is my bit 3 is equal to my bit 2. So we are just reading a switch, and we want to store that switch value, whether it is logic 1 or whether it is a logic 0, that is within a my bit 3. After that, in the next line, we are just complementing that bit, and we are passing it to the my bit 1. So here I will explain once again that my bit 2 is nothing but a switch. So we are reading just reading a switch, and we are passing that value to the internal memory area. Now in the next line, we are just reading that bit, we are complementing it, and we are passing it to the port number 1 and the line number 0. Now let us try and simulate this program in a kill compiler. Now let us try and simulate this program. So I have already added this assignment number 16 within a kill compiler. So first of all we have to compile this. Okay, so we have a 0 error and 0 warning so that we can simulate this program. So as you know that, we have to imagine that here we have connected an LED. Now here at port number 2.7 we have connected an switch, and the next SBC variable that we have used as a memory bit, because before performing any XOR operation or the NOT operation or even an arithmetic operation, we have to store that data, and after storing the data we can modify that data. So here one more thing that you have to look at is this for loop. So this for loop is nothing but an infinite loop. So instead of using a while one, we have used a for loop over here. We have not given an initial condition and the final condition, so that is why it will be an infinite loop. So we have already compiled this program, so let us run this program in a debug mode and try to look at the output. So I'll now close down this. We don't require port number 0, we require port 1, and we require port number 2. So we go to the peripherals, IO ports, and here is your port number 2. So at port number 2 we have connected a switch, and port number 1 we have connected an LED. So that we have to check on. So I'll go in a stepwise mode. So in the first cycle, as you can see that it is assigned 1, and by default all these ports are 1, so 1 will be assigned to the 1. So this is our first cycle. Now let us make this 2.7 as a 0 and try to look at the output. So here you can see that port number 1 line number 0 is also become an 0. So let us make it 1, and here you can see that it has become a 0. So as we are using a NOT operation, so whenever it is 1 it becomes a 0, and whenever it is a 0, in that case it becomes a 1. So as we are using a pull-up register, that is why we have to complement these bits to show the status. So once again we can simulate this program. So when I am giving a 1, it is becoming a 0. So when I am making it 0, it's becoming a 1. So this is how the NOT operator works. So this is for the assignment number 16. So I'll stop this program by stopping this debug mode, and this is for your assignment number 16.